Previously on this channel, we covered work and energy, how to get an office, and how to use as much energy as possible while you're in that office. No? Oh, yeah, I remember now. We were talking about work and energy as in the physics terms. Yeah, now I understand. But in that video, I was hinting at something called conservation of energy. And that is what we are talking about in this video today. So let's go into it. Well, what does conservation of energy say? Well, first, let me correct myself. Conservation of energy is a universal law in this universe. But besides that, what we're going to talk about today is mechanical conservation of energy, or conservation of mechanical energy. But right now, you don't need to know that completely. So, what is this? Well, this says that the initial potential energy, which is notated as U, earlier I said PE, but it's also notated as U, plus initial kinetic energy is equal to final kinetic energy final potential plus final kinetic energy minus all non-conservative forces doing work. And examples of these would be friction, etc. But for this video, for explaining this topic, we're not going to pay much attention to this, and it's not going to be really used until a little later in this series. So, let's move on to actually applying it. But before we do that, a quick overview of a potential and kinetic energy. This is mgh, and this is, half mv squared. But the thing about this is the reason it says conservation of mechanical energy, because potential energy plus kinetic energy is equal to mechanical energy, or ME. So, there you have it. That's just a quick overview of what the conservation of energy is. Now, it might not seem very complicated or very useful at all, but this can massively simplify your life when you are working with things falling over a distance or on other things. And what better way to show you than to do 2 examples explaining this same conservation of energy. Alright, this problem says a ball is falling from a height h. Air resistance is negligible. What is the speed of the ball right before it hits the ground? Now, if we were to solve this using regular forces, this would be almost impossible. Because first we'd have to measure, we have the downward force G, there's no air resistance, then the speed gets faster and faster. But then over what time? We'd have to use a large combination of the big 5 equations. But instead of that, what we can do is we can just use conservation of energy. So at the beginning, since it's at rest, or I should probably add that, starts at rest, that was my intention for this problem. Since this starts at rest, we know that before it was launched, it had potential energy at a height h. So our potential energy would be mgh. And since it's at rest, there's no velocity, meaning no kinetic energy. So our initial mechanical energy is equal to mgh plus 0, or just mgh. Now, next, what we have is our final mechanical energy, mf. Now, since right before it hits the ground, it's essentially at height 0, we're going to have no potential energy. But we're going to have all of that be converted into kinetic energy with our final velocity and our mass. Now, since there's no air resistance or any other non-conservative forces, you can just set these equal to each other. So, mgh is equal to 1/2 of mv squared. Now solving for this gives us v squared is equal to, canceling out the m's and multiplying by 2 is 2gh, and taking the square root of that gives us the square root of 2gh. And look at how simple that was. But this is where the power, the real power, the real usefulness of this comes in. Since energy can't be created or destroyed, that means we can just put everything in terms of energy. We can solve for anything we want to solve for. Since energy is the one thing that stays constant, we don't have to solve for anything else. We already have a sort of reference frame or a basis to solve everything from. And besides that, it has super deep implications about the universe and how it let all of reality exist and stuff. But that's not completely important right now. I'm here to teach you how you can practically use these concepts. So there's our first problem. Let's move on to our second problem. Alright, over here we have a block of mass m slides down a frictionless ramp of height h and then goes through a loop of radius r. What is the minimum height h in terms of r that would allow the block to complete the loop without falling off? No non-conservative forces. Now, if you try to solve it with force, there's already a problem. How long is the ramp? How much distance is it carrying? And how much distance is it carrying? And to know that, we need to know the angle. But we don't know the angle, and I'm not about to give you the angle. So, what do we do now? We turn to the other tools in our pocket. Energy. But before you use energy, there is a small bit of force analysis that we have to do. When we draw this over here, when we draw our figure, we have our ramp of height h. Then we have our loop. I know it's not a perfect circle, but assume it's a perfect circle of radius r, and then it goes back down. Now, over here, let me redraw that. So, over here we have our diagram, h and r, after I redrew it. So, what we realize is when we're in the loop, it needs to pass through the top of the loop, where the force pulling downwards and away is the strongest, as gravity is the only other force. Now, in order to balance that force, we need a minimum speed that it's going to need to have. So, if we draw another diagram, zooming in on the loop, and we have our block over here, we have its weight pulling downwards, and the normal force going upwards, or the velocity going towards the left, which is our minimum speed. And we have our velocity on the left-hand side. But also, since gravity is the only force, this force must equal the centripetal force, which is the force towards the center. So, then, solving for that force, solving for the velocity for that force, we get v squared is equal to gr, and v is equal to the square root of gr. So, now that we have the square root of gr and we know our minimum speed, we can use conservation of energy. Since it starts from rest at the top, which also should be assumed, we have mgh is then equal to what we have is at the bottom of the loop, at the minimum speed, so it's going to be 1/2 of mass times our minimum speed, gr squared, plus, since at the top of the loop is the hardest place to pass, that height is going to be 2r, the potential energy will be mg 2r. Now, we know exactly what we need to solve for, and we have everything in this equation. Because we have our initial energy and our final energy, which is our kinetic energy, plus the potential energy at that point. So, solving, canceling out m and then squaring this, so removing the square root and the square, erasing that, then canceling out g from everywhere. That gets us h is equal to 1/2 r plus 2r. So h then becomes 5/2r. And there you have it, the solution to our second problem, made infinitely easier, literally because it would be infinitely difficult to solve it with forces, as I don't think it would even be possible to solve it with forces. So, there you have it, a true example of why conservation of energy is just so powerful. So, if you enjoyed this video and learned something new, which should be the goal of everyone, to learn something new, please make sure to like and subscribe and hit that notification button for more awesome videos just like this, and make sure to comment down below for any suggestions you have for this channel. Besides that, you guys are the best part of what I do. Thank you so much for watching. See you in the next one, and bye-bye.